Hello, good morning, students. It's today 4th of April 2020, and here again I am with another problem on cooling tubes. So, the problem is, as you can see, we will be solving two problems. This is the problem number second, and this is the problem number one. So, the problem reads like today we are 4th April 2020, and this is problem on cooling tube. So this is a V2 exam problem. It has appeared in a V2 exam in 2012, and similar problems are appearing in various exams in 12, 15, 17. So this is one problem. So let's see the problem. Let's read the problem. What the problem states: the problem states, first, the full load efficiency of a 300 kVA single phase core type transformer is 98.2% at unity power factor. UPF means unity power factor. Design the number of cooling tubes. Design the number of cooling tubes necessary if the temperature rise is 35 degrees Celsius. The tank area may be assumed as 4.92 meter square. Assume the tube diameter as 5 centimeter and average length of 105 centimeter. Heat dissipation may be assumed as 12.5 per meter square per degree Celsius. So this heat dissipation is due to radiation and convection. Radiation and convection. We know that because of radiation there is 6 meter square per degree Celsius, and because of this convection there is 6.5 meter square per degree Celsius. Time again I have mentioned, whenever we are given any problem, so we have to infer from that, what is the data given. So first of all we'll read the data given, that is given data. So what we see here from the data, we see it has mentioned this transformer is a single phase transformer. It is KVA rating is 300. So we can write down KVA rating as 300. Another thing, it's a unity power factor, so cos phi would be equal to 1. And design the number of cooling tubes if the temperature rises 35 degrees Celsius. Okay, three phase, single phase, so single phase transformer. One more thing we have, and the efficiency is represented by neta. This is 98.2%. Okay, and what else we are having? We are having the temperature rise, that is our theta as 35. Theta we can write as 35. And what else we do have? We have the surface area is also given. The surface area ST is given, that is 4.92 meters square. Apart from that, what else is given? Yes, pi. See, area of a tube in my previous lectures, if you go and see, was given by pi dt lt. So this is pi dt lt. So what is dt? How much is the diameter given? Diameter, it is mentioned, this is 5 centimeters, and lt is given as 105 centimeters. Of course the dimensions, we have to convert each and every dimension into meter. So that is the whole data. Apart from that, we are having this 12.5, so that we know. So how do we go about this problem? The main dimensions or the main formulas which we have calculated in the previous section, if you go back to my earlier videos, you can relate to it. I will be not be solving the formula, I will be directly substituting the formula. So we have this particular term called efficiency. So everybody knows efficiency is what? How efficiency is given? Obviously it is given as output by input, output power by input power. So my efficiency is mentioned over here. It is given output power by input power. Now, do I have anything? Do I have output power? Can I calculate my output power? So power unit is kW. So how can I represent kW? kW. If you see here, how can I represent my kW? Kw can be represented. Now I'll be moving to this page. So if I want to represent my kW, I can write my kW is equal to kVA cos phi. kVA cos phi. Simple. You have your this power triangle. If you write like this, I have a triangle. Okay. From this power triangle, you can write your theta is this. Okay. Your kVA is this, and your cos of phi. Cos phi is your base by half hypotenuse. So base is your kW, and this is kVAR. So this is your reactive power. This is your real power. So your base is kW, your hypotenuse is kVA. So you can write kW is equal to kVA cos phi. Same thing, you can represent this like this also, where kW is P, this is Q, this is S. This is nothing but as Q, this is nothing but as P, and this is nothing but as S. So you can write S is equal to S square is equal to P square plus Q square, or in other terms S is equal to under root of P square plus Q square. So we are interested to calculate this. So do we have kVA? Yes, we have kVA. It's given from the given data. We have kVA. kVA is how much? 300. So can we substitute here? Yes, we can substitute here. How much is 300 kV? And what is the value? This into 1. So this comes out around 300. So your efficiency is output power by input power. So your output power is 300, input power is 300 plus losses. So already the value of efficiency is given 98 point, how much it is given? 98.2%. 300 divided by 300 plus losses. So from this formula, if you cross multiply, you will get 98.2 into 300 plus losses is equal to 300. Here you can write 300 plus losses is equal to 300 divided by 98.2, and losses would be equal to 300 divided by 98.2 minus 300. So you will get one particular value for this, and after solving, the value of losses which you are arriving is, this is your losses. So losses would be around 5.5 kW. 5.5 kW. This multiplied by this and minus this divided by this. So you get around 5.5 kW. You can calculate it. And now simple substitution. You know losses is nothing but Pi plus Pc. So the other day I have derived the formula for the number of tubes, that was area of the tube, area of the dissipating surface divided by the area of one particular tube. So directly I am going to write the formula for number of tubes. So number of tubes is equal to, how much is it is equal to? It is equal to, straight away we will write 8.8 pi times dt LT Pi plus Pc divided by theta minus 12.5 times St. So St value also it is given there, and theta value also it is given there, and dt is 5 centimeter. So dt we have to convert into meter. 5 centimeter, if you have to convert into meter, 5 in 10 power minus 2 meter, because 1 centimeter would be 10 power minus 2 meter. Similarly LT is how much? 105 centimeter. 105 centimeter, how will you write? 105 in 10 power minus 2 meter. So this would be 1.05. This would be 105 divided by 100. So this is 1.05. So this is 1.05 centimeter. Again we have all the values, so we can calculate the number of tubes. So this is 1 divided by 8.8 pi. Instead of dt we are going to write 0.05. Instead of lt we are going to write 1.05, because we have to keep the unit into consideration. This is in meter square, and here also we have 5.5 in 10 power 3, because this is in kilowatts, so hence in watts we have to write divided by 35 minus 12.5 and into 4.92. What we will get now, we will get the number of tubes by solving this, and I hope the answer you will get is around, this would be around 0.689 into 157.14 minus 61.5. so it comes around near to the some fraction value. It will come, we'll take an integer value, so the number of tubes is 66 tubes. So this is one way to solve the problem. Let's see one more problem on the number of tubes. So the one more problem which we have taken is, see, this was a direct substitution. Of course you have to remember the formulas for the examination or the derivation also, because the derivation, sometimes they can ask you the derivation, sometimes they can ask you the problem straight away. It is better that you understand the concept also, which you can follow in my previous lectures, and you can also keep, for examination point of view, some mnemonic techniques to remember the formulas, which if you have less time you can directly apply the formula and get the answer. So one more problem we'll be going around about is the second problem which we'll be seeing is, this problem states, design a cooling system for a natural oil cooled transformer of rating 1200 kVA with its main dimension as 0.6 into 1.5 into 1.8 meter. So the dimension is every dimension is length, breadth and height respectively. The full load loss is 12 kilowatts. Take loss dissipation due to radiation and convection as 6 watts per meter square per degree Celsius and 6.5 watts per meter square per degree Celsius, and 35% improvement in convection is to be provided by tubes. So allowable temperature rise is 40 degree. Use cooling tubes of 5 centimeter diameter and 1 meter length. So this will be your this D, and this would be your LT. So area of a cooling tube, if you have to calculate, this would be again pi dt LT. So again, first going to that, directly jumping into that, let's first see what values we are given here. So after I finish, so first of all, to solve any problem we have to write the given data, carefully read problem once, twice before attempting. First you have to think inside your mind, then you have to slowly, you have to calm down, and you don't have to get excited, and you have to read it carefully once, twice, and then you have to ink your what do I say, paper. So rating of a transformer, that is kVA rating of a transformer is given. Rating of transformer is given. How much it is? Tell me please. The rating of a transformer, it is how much? 1200 kVA. Yes, you are correct, 1200 kVA. And the second value what we are going to see, the main dimensions. So the main dimensions are given there. By now half of the class would have written the main dimensions. So the main dimensions are 0.6 into 1.5 into 1.8. so there is no clearance mentioned as such here. If there was some clearance mentioned, so we have to add clearance to this value. Herein they have not mentioned any clearance, so this is your length, breadth and your height, and your full load loss is given. Your full load loss is given, full load loss. So your full load loss is how much? 12 kilowatts. Okay, then your temperature rise is given, and improvement in convection. So temperature rise theta is 40 degree, and improvement in convection, so this would come around the same 8.8 only, because already in the previous derivations also we have seen. So usually improvement in convection, they are considering it to be around 35% only. So how do we go about the problem? The first thing we are interested is to calculate the total heat dissipating surface. So my total heat dissipating surface would be, how much it would be? See, first of all we have to see here what is this. Here you see this is your LT, this is your HT, and this is your WT. So total heat dissipating surface would be HTLT and HTWT. That is your S would be twice HTLT plus HTWT. So your HT is how much? HT is 1.5, 1.5, and sorry, your HTLT, so HTLT, so 1.8 into 0.6. This is your LT and this is your C. If you read carefully, this is your length is 0.6, length is 0.6, your breadth is 1.5. So this is your WT is your 1.5, and 1.8 is your height. This is your HT. 1.8 is your height. So if you have to read carefully what is what. So here you can write twice your HT is how much? 1.8. Your LT is how much? LT is, please tell me, 0.6. LT is 0.6. And how much is your HT again? HT is again 1.8, and your 1.8, and your WT is 1.5 into 1.5. So if we go for the calculation of this, twice into 1.8 into 0.6 plus 1.8 into 1.5, so you get around ST is equal to 7.56 meters square. So we'll move to the next page. So your ST is equal to, so your ST would be equal to 7.56 meters square. So the ST is equal to 7.56 meter. Your ST is equal to 7.56 meter square. So now we are interested in interested to calculate the loss dissipation due to radiation and convection. So loss dissipation due to radiation and convection is 12.5 ST times. So loss dissipation due to radiation and convection due to radiation and convection are 12.5 ST, R 12.5 ST, R 12.5 ST, R 12.5 ST times, R 12.5 ST times. So this is your 12.5 ST times. So your heat dissipate 12.5 ST. So this is your surface area you are getting. I'll just be explaining you. So sorry, there was some technical problem. Yeah. So your loss dissipation is how much? 12.5 ST times. Now your heat dissipating area of tubes, that is your AT, is given that 40% improvement in dissipation, 35% improvement due to convection is to be provided by tubes of area 80. So we already know, let's suppose heat dissipating area of tubes is 80. Let us suppose heat dissipating area of tubes is 80. So due to the tubes, the dissipation occurs only due to the convection. So due to the tubes, it would be 6.5 times the heat dissipation would be. Loss dissipated due to cooling tubes would be 6.5 times of 80, and plus there is how much? 35% improvement. So 35% improvement we can represent into 1.35, that comes around 8.77 times 80. So what we can see, as from our previous definition, we can see the total losses dissipating area by tanks and tubes. So total losses dissipating dissipating area by tanks and tubes, it happens to be how much? 12.5 st times plus 8.7780. so this st value we have calculated, and this total losses would be 12.5 st times how much, and we have to consider the temperature also in this particular case. This is 12.5 st times theta and theta. So the total losses are mentioned there, that is 12 kilowatts. 12 kilowatts is equal to your 12.5 st plus 8.7780 theta. We can take outside. The value of theta also is mentioned, it is 40, and other values also we are having. This kilowatt can be represented 12 into 1000 because 1 kilowatt is 1000 watts, and 12.5 st we have taken plus 8.7780, and theta value is also given 40. Only value we require is 80 because st value also we have calculated, it's around 7.56 meter square. So we can directly write 40, we take this equation this side, 40 is equal to 12,000 divided by 12.5. instead of st we directly take the value 7.56 and plus 8.7780. so now obviously we have the value, we cross multiply and we get the value of 80. so the value of 80 would be around 23.43 meter square. So area of tubes, the number of tubes, total area, this is total area of the tubes, this is total area of tubes, happens to be 23.43 meter square. Now number of tubes would be how much? Number of tubes would be total area of tubes, that is total area of tubes 80 divided by area of each tube, if area of each tube is represented by small 80, so area of each tube we can calculate. How do we go about area of each tube? We have in the earlier only case only, in the previous section only, I have shown you the area of each tube would be pi dtlt. This is 5, this can be represented by 0.05, and this is directly given as 1 meter. So we can calculate area of each tube. So area of each tube happens to be here in this particular case. So we have arrived at area of each tube happens to be how much? It happens to be, we can calculate the value of area of each tube. Area of each tube is area of each tube is pi dt lt. So the value of dt is 5 centimeter 10 power minus 2, and this is 1 meter, it's already given, so it will remain as it is. So pi into 0.05 into 1, this is around 0.157 meter square. And now total number of tubes, happens to be how much? The earlier value was 23.43 and 0.157 meter square, so this happens to be around 149. Now let's see the arrangement. If we consider, let 7.5 centimeter be the center to center distance between the cooling tubes. So let 7.5 centimeter be the center to center distance between the cooling tubes. So between the cooling tubes, so what does this represent? This represents means how many cooling tubes. So 159, let's suppose we had now we have to take into consideration what is our length and breadth. So in the earlier case only we have seen, here only I have told you. So my length happens to be in this case 60 centimeter. This is my length is my 60 centimeter, and my breadth happens to be 1.5. so breadth, so length is how much? Length it gives is 0.6 meters, which can be represented as 0.6 into 100 centimeter. This is around 60 centimeter. Similarly, my breadth, how can I represent? Breadth is equal to 1.5 meter, that is 1.5 into 100, that is 150 centimeter, that is 150 centimeter. So I can design my tank, and around the tank, around the length and breadth of the tank, I have to arrange my tubes. So if this is my tank like this, so I have a dimension, this is my 60 centimeter, this is my width, or I can say it is a breadth or width, whatever. Different books have different symbols, no problem. And this is my length, this happens to be around 150 centimeter. Now if the distance between the center to center happens to be around 7.5, so around the length, how many tubes will be there? It would be 150 divided by 7.5. Around the breadth, how many tubes would be there? It would be 60 divided by 7.5. So this happens to be around 20, and this happens to be around 8. So the number of tubes which I calculated is 149. So if I take into consideration, if I number of tubes in each row will be, if I keep this 20 plus 8 into 2, so number of tubes in each row is 56. Oh, okay. Now if two row of tubes are placed, now if another row, if I place one more row, it would be how much? 20 plus 8 into 2, it would be another 56. So this total happens to be 112. What we have to do is, since we have calculated 149 tubes, this is the economic size that will help the transformer to cool down, and it will not help, it does not result into any short circuit or anything due to the heat and transformer bursting. Hence we have to kept into consideration all the economics. The number of tubes should be around this figure or more than it. It should not be less than it, because we have to maintain the temperature and everything. We should not have to maintain the thermal considerations. So 112 happens to be a little small number. So what we do is that, since we have calculated roughly 149 tubes, let's place these tubes. How do we place these tubes? Let's place these tubes in length. Let's place it as 20, 16 and 20. See here, around the length 20, like this, 20, 16 and 20. So 20, 16 and 20 happens to be around 56. Here also same thing, 20, 16 and 20. So this 56 happens to be 112. And now what should we do around the breadth? We should establish. So let's establish here one around 8. Let's give here some 4, another 8. So this is how much? This is around 20. So this is around 20, 8, 4 and 8, and 20 tubes on this side, and total we are having 112. 112 plus 20 is how much? 132. And another 20 we'll put here, same, 8, 4, another 8. So here 20. So what we are seeing around the length, here 20 on one side, here 20, this happens to be 40, here 56, here 56, this is 112. So we can say 112 plus 40, it happens to be 152. How much we calculated? 149. Okay, we are getting 3 tubes more, 152, but we have keeping a radial arrangement so that the balance of heat is maintained. So okay, 3 more tubes will incorporate for an optimum design, and this would be the best design for this transformer configuration. If they have not asked you how to design and how to put the tubes across the rectangular section or the transformer for optimum design, no need, you can stop at 149. If they have asked, you can further proceed and you can calculate around that figure, and the mathematical manipulation you can do, And what you have to keep into consideration, since your length is greater, so more the number of tubes will be across the length and the height section, because this your height would be get automatically divided by your 7.5. In some books or some examination questions, they will give you the length between center to center distance between the tube as 7.5 or 7. If they have not given, you can consider it as 7.5. And if they have not given this convection due to the tubes, obviously you know that is 6.5. And if they have not given, you can directly take it as 12.5 due to the tubes and the tanks, because it is already given. So what we have seen is, we have seen in every problem, first we have calculating the area due to the tank, and that area due to the tank and the loss dissipated due to the tank is 12.5 times st. St is what? St is the total surface area of the tank. Obviously we are not taking the bottom surface area, we are just taking the top surface area and the sideways, so that's why the bottom is not incorporated, hence the other factor is not seen there. And what we are doing is, we are calculating the total loss dissipated due to convection and radiation. So the total loss dissipated in the tank would be 12.5 times st. Then the total loss due to the tank and tubes would be, so we are considering the area due to tube, the loss would be 6.5 times, because it only takes convection into place. 6.5 times 80, and of course the total loss, you have to multiply it with the temperature, and you will get by substituting the formulas, and eventually you arrive at this particular thing. What you have what I will like is that I'll be giving you some assignment in my next class. I want you to watch these videos pretty carefully, and in my Google Classroom, I just want you to solve some assignments. And since I've for every person, it would be a unique assignment, and length and dimensions and breadth would be based upon his height and his measurements and his date of birth. Different denominations I'll be using, so I want a unique answer. Every person will be having a unique answer. I want you people to really work hard, and I'll be keeping some marks for this assignment also. Hope you are doing well, studying well, and let's meet in the next class. Thank you very much.